or get close to finishing up graphical models. And then I'm going to post very soon, probably later today or tomorrow, some notes on the next topic, which is dimension reduction. And so watch for those. When we do dimension reduction, we'll start by doing what we might call traditional dimension reduction. These are things like multidimensional scaling of principal components. Then we're going to move on to some modern topics, which include random projections, which are kind of an important thing these days, and something called Johnson-Linden-Strauss. And it's pretty amazing stuff. It shows that if we take random projections of high-dimensional vectors, then by using some simple concentration of measure results, we can show that we preserve a lot of the information when we take these projections. Okay, so that'll go up. Either that'll be one set of notes, or I might break it up into two sets of notes. We'll see. But expect that to go up pretty soon. Okay? And then we'll do some of the other remaining topics. Remember that the last week is the course conference. So let me tell you how we're going to do that. We've done this many times in the past, and it's always been a big hit. And what happens is each team, what you're going to get is 2 minutes to present your paper and 2 slides. So these are sometimes called blitz talks. You know, they have them at conferences sometimes. And actually, today I don't know if you know about it, but there's an inter-university contest they have called the 3-minute thesis, where you get to present your whole thesis in 3 minutes in 1 slide. And I think maybe the finals or semifinals are today in the Economy Auditorium at 4:30. So if you want to see people who are really good at this, check that out today. It's a very, very, very good skill to have, to be able to, you know, how can I summarize what I want to say in 1 or 2 minutes? It's not easy. And all you can really do is a little advertisement for here's sort of what I worked on, and here's kind of the main idea of it. But it's a lot of fun. We give out a trophy and everything. And but what will happen is before we do it, you'll each send by PDF your 2 slides to the TAs, and then they'll be here, and they'll be showing them on the screen. And then when your 2 minutes are up, bang, that's it. They just take it down, and the next person comes up. You know, we have like a big hook that pulls you off the... so it's actually a lot of fun. And you'd be surprised how much, you know, it's hard, but you'd be surprised how much you can see in 1 or 2 minutes. It's really, it's a good skill to develop. Okay, so that'll be the last week, the last 2 classes. All right, and we have a few more topics to go before that. So we were almost finished talking about these correlation graphs. Then we have to talk about partial correlation graphs and conditional independence graphs. Remember that there's many different types of correlation graphs. We talked about Pearson correlation, Kendall-Tau correlation, the distance correlation, and the corresponding reproducing kernel Hilbert space correlations, and the tau squared. And one thing I mentioned about these different correlations is that one problem is getting confidence intervals. We know how to do tests. We can always do a permutation test. But to get a confidence interval, we typically need like a limiting distribution. The limiting distribution, as we saw for some of these things, in particular for these 2, is different under the null hypothesis than under the alternative. Under the alternative, there's no correlation. Then we have things like this goes to some sort of normal distribution with some mean, some variance, which means you can use normal confidence intervals or bootstrapping. But under the null hypothesis, the convergence was to something, I called it a Gaussian chaos. It's written there for you in the middle of page 7. It's a linear combination of chi-squareds. Actually looks like this here. Each z is a standard normal. And this distribution is kind of useless because it involves an infinite sum, and there's parameters in it that we don't know. So I think, did I mention the blocking idea last time? I think I did. That was the last thing I mentioned. So you can form these blocks and form an unused statistic. You can de-statisticify it or something, whatever the right verb would be. That loses some efficiency, but it does give you valid confidence intervals. I did want to mention one more thing, which is because this is a used statistic and it's bounded, we can get a confidence interval another way, which is this is a chance for me to teach you something we haven't done yet in the course, which is Hoeffding's inequality for used statistics. One thing that people often don't realize is Hoeffding's original paper was not just about that basic inequality we learned. It was actually about concentration measure for these U statistics. Let me remind you what a U statistic is. Remember that an average is just something that looks like this, whereas a U statistic might involve pairs or triples or whatever. This becomes 1 over n, choose 2. Or more generally, 1 over n, choose b, let's say. Where these are over distinct pairs, or not pairs, but groups of b. That's an order statistic, a U statistic of order b. And if you remember back to the definition of tau star, if you look back at the definition, it could be written that way. It could be written as a sum of, let's say, k of zi, zj, zk, zl over groups of 4 observations, quadruples. But if you look back to the definition, these are all bounded by -1 and 1. Unlike the distance correlation, which could be written as a U statistic, but it was unbounded. It involved things like xi minus xj, which can be unbounded. This was all about signs of things. Remember sine of this plus this minus this. So sine is either +1 or -1. So it turns out that, first of all, this is easily seen to be a unbiased estimator. But now I want to know, remember Hoeffding's inequality said that if I have an average minus the expected value of that average, that's less than or equal to something like 2e to the minus 2n epsilon squared, maybe another constant, depending on what range x can be. But actually, it turns out this theorem holds for U statistics, too. The only difference is this. So I'm going to tell you, there it is. It's in the top of page 8. This is Hoeffding's inequality. The only thing that changes is, instead of having 2 n, so actually let me put up, this is b minus a squared, right? This is just the range that x can take. It looks exactly the same. It's 2n t squared over b minus a squared. I'm using b twice, unfortunately. Let me give this a different name now. Let's call it k. No, I've already used k. What haven't I used yet? How about Greek letter? All right. Beta. Okay. Because that's what goes here. That's all that changes in Hoeffding's inequality. Okay. So in our case, for this thing, beta is 4. And since this goes from -1 to +1, this is 2. So this is 2 squared. So we get 2e to the minus n t squared over 8. And since we have a U statistic with bounded range, we just use Hoeffding's inequality and we can set this equal to alpha and we get a confidence interval. So if I solve now for t, you're going to get t equal to 8 over n. And so that gives us a confidence interval for the tau squared statistic. But this doesn't work for the distance correlation. It doesn't work for the reproducing kernel Hilbert space thing, I don't think. Actually, that's a good question. Does it work for the reproducing kernel Hilbert space correlations? I need to think about that one. Anyway, I've given you way too much information probably about these different correlations. You're having correlations coming out of your ears, but when you go to do this, you're just going to pick one and do it and, again, make a graph out of it. The whole point here was to construct a graph. But this was partly just an excuse for me to slip in a little piece of information, which is that Hoeffding's inequality is more general than we made it out to be. But I also wanted to use this as an opportunity to talk about something else, which is the high-dimensional bootstrap. So again, I'm using this really as just an excuse to do that, but let's suppose you decided to use Pearson correlation. And whatever limitations Pearson correlation has, it's probably still the most commonly used correlation. If you look at a lot of bioinformatics papers, there's a lot of graphs constructed just using Pearson correlation. And if we really want to get a valid confidence set, well, one thing we could do is we had a way of doing a normal approximation for rho, but then you had to do some sort of Bonferroni correction for the fact that you're doing d squared different correlations. You wonder maybe you can do better by just doing some overall calculation. And we can. We can use something that was only verified in about 2 years ago, which is the high-dimensional bootstrap. And really think of this as something you can use in many, many other situations. So this is just going to be an example. What's going on out there? This is an example of something that's just more general, which is whenever we're doing high-dimensional statistics, there are certain situations now where we can use the bootstrap. So how is this going to work? So remember, we're trying to construct a graph, a correlation graph. I want to connect any two nodes, and we're going to use Pearson correlation again. So I want to connect two nodes if the Pearson correlation between feature j and feature k is sufficiently big. Maybe significantly different than 0, or maybe even bigger than some threshold epsilon. So so one thing I might want to do is construct these confidence intervals for every possible pair. So here's how we're going to do it. I'm going to construct all of the correlations. So let's do it this way. Let's define R to be the matrix. This is a D by D matrix of all the true correlations. Between every pair of genes, let's say they're genes, there's some true correlation, okay? And so that's an unknown matrix, and it's got d squared, or order d squared parameters in it. Between each pair, I can get an estimate. Just the sample correlation. So what I'm going to try to do is try to get a measure of how far is this from this. Simultaneously over all edges in the graph, over all possible correlations. And the amazing thing is we can do this with the bootstrap if we do it a certain way. So here we go. Suppose that I knew, let me define f of t to be the probability of the square root of n. And what I'm going to do is take the maximum between all these things. So I'm going to look at the maximum over all jk. Let's do it this way, yeah. So I'm looking at the difference between the estimate and the truth, and I'm taking the maximum over all of them. And it's really important that I'm taking the maximum. And I'll explain why in a minute. It's important actually for theoretical reasons and for practical reasons. The practical reason is this is going to allow me to construct a confidence rectangle, hyperrectangle, or hypercube around all of the rows, which also gives me a confidence interval for each individual one simultaneously. So just to give you a picture of that, if I give you, there's d squared parameters, but suppose there was only 2 parameters. So suppose there was only 2 parameters. I'm going to construct a confidence cube, or confidence rectangle. It's going to be a confidence set for the entire vector, or matrix in this case, of d squared parameters. What that means, though, is I can read off a confidence interval immediately for this guy and this guy automatically if it's in the form of a rectangle. If I tried to use a confidence sphere or ellipsoid, it turns out that it's not going to work, that the bootstrap theorem is going to fail for some very deep reasons that have to do with high dimensional probability theory. So we're going to be doing this. And it's clear if I knew this distribution, all I'd have to do is find the correct cutoff value. In other words, if I now took, let's look at rho hat j. Let's find the, did I give it a name? Yes. Let's take the 1 minus alpha quantile. So this unknown distribution function looks something like this. Let's find the alpha quantile. Then with probability 1 minus alpha, we know that the maximum is always less than or equal to that quantity. So I can take this minus W alpha over root n and rho hat that is an asymptotic, let's call this CJK. That's an asymptotic 1 minus alpha confidence interval for the jkth thing. But this is, because it's with respect to the max, it's simultaneously for all pairs. So the cool thing about this, let me state the result, is that as long as the dimension is smaller than e to the n to the 1/6, we'll come back to that in a minute, the probability that rho jk is in that confidence interval for all of the nodes on your graph, for all jk, converges to 1 minus alpha as n goes to infinity. The important thing is this. Look how big d can be relative to n. If I told you d had to be less than, n to the 1/4, let's say, that wouldn't be very good, right? You couldn't handle very high dimensional problems. And up until 2 years ago, that was the situation. Actually, it was more like, actually, it was, I think the best known result up until a few years ago was something like n to the 1/7, which is almost a constant. I mean, n to the 1/7 is pretty close to constant. And so it used to be that the previous results about the bootstrap were that, I haven't done the bootstrap yet, and I'm going to, sorry, I didn't quite finish that. I'll come back to that in a minute. But if it was like this, it would be bad. But now it's exponential in the dimension. This was a huge, huge, very recent breakthrough. I didn't tell you what the result was. I'm sorry. This confidence interval, if I could construct it, would be exact. What I really want to do is put in estimates, because we don't know this distribution. And the amazing thing is I can just do it with the bootstrap the way we learned how to do it in 705, as long as we stick to the max. So here's how we do it. We take our data. What are we calling our data? Let's say y1 to yn. And we form, as usual, the empirical distribution, which puts mass 1 over n at each data point. And now we just do the bootstrap thing. Remember how that worked? We draw n observations from the empirical distribution, which is equivalent to resampling the data with replacement n times. We recompute the matrix of correlations. And then we repeat this many times, right? So we go r hat 1 star up to r hat b. And then we estimate fn with fn hat, which is just how often in the bootstrap sampling did this compared to this end up being less than t. This is just the bootstrap empirical distribution. The key again is that the measure of distance we're using is the maximum over all the graph, over all pairs of edges. Right, so you just sample the data, get a new r hat, repeat. That gives you an empirical distribution. You find the 95% quantile, and you form this confidence interval for each pair, and then you get simultaneous confidence intervals. At least, I mean, they're asymptotically valid. This is not a finite sample. And it doesn't apply, again, just to correlations. I just happened to thought this was a good chance to introduce this. But you can do this for many, many other things that come up. As long as the dimension is not growing super fast in the sample size, we still get the validity of the bootstrap in high dimensions. Okay? And the proof that this is valid is extremely difficult, I'll warn you, but it's very interesting. If you want to see it, it's I'm going to say 2012, maybe 13, something like that. So I guess that's 4 years ago now.
Is there some intuition over the 1/6?
No. So the 1/6 is a bit mysterious, actually. It comes out of the proof, and it seems that it can't be improved. There's some evidence that it can't be improved. But the problem is we're getting into high-dimensional probability theory where there's a lot of mysterious things. And so, yeah, let's just say that it's not intuitive at all. At least I don't find it intuitive. It just comes out of the proof. That's what you need. But again, the important thing here is that the dimension can grow so big. In fact, let me say something else. How far is this true coverage probability from 1 minus alpha? What is the actual error? And I'll tell you what it is. It's log d to the 7th over n to the 1/6. So actually the error goes to 0 kind of slowly, although in practice this seems to work well. There's some weird things going on here, but here's the important thing. It's log d. Again, up until this paper, it was d. Now it's log d, a huge, huge breakthrough. And the 6 is a bit mysterious, although there seems to be a proof that you can't get rid of it. Yeah. It's a whole fascinating area, this high-dimensional bootstrap stuff. And all very, very, very recent stuff. So anyway, that's a way to construct a graph, though, that's very fast, because there's no permutation test to do anymore. There is a bootstrap, but this is doing it simultaneously for all edges of the graph. Because what you get out when you're done is a confidence interval for each and every pair in the graph. And now you can just check. You pick a threshold epsilon, and if the confidence interval excludes that interval from minus epsilon to epsilon, you can connect the graph or not. I think I even put a few examples. Although I'm not sure. We probably looked at these. Did I show you these examples yet? No, I didn't. So you can see some examples. This is page 9, figure 2. I just picked 4 examples here. These are Pearson correlation graphs. And this is what comes out. Let me explain what the examples were. Let's see here. All right. It would be interesting to do these with the other correlations as well. So the first one is actually 2 Markov chains. So I have a bunch of variables, a bunch of features. And I have a Markov chain here. So think of this feature has a distribution, then we draw this feature given this feature, this one given this feature, and so on. So when we get to conditional independence, that's what the graph will look like. But we're not doing that, right? We're doing correlation graphs. I'm saying which things are correlated with other things. And even though this transition goes from here to here and here to here, this makes these correlated. So everything's actually connected to everything else here, and same here. And that's what you get. This is the the top right was what's called a hub, where you have something, a feature, and then you have another feature whose distribution depends on that, and another feature that depends on that, and so on. And it recovered it pretty good. I mean, there's a few extra edges there, but the bottom left was just 4 small groups of highly correlated variables, which it recovered perfectly. And the bottom right was a banded covariance matrix. Imagine a matrix that looks like this. There's going to be the variances down here, and say, I'm also going to put some variances here so that 2 is correlated to 1, 3 is correlated to 2, but these are all going to be 0. And this is the kind of structure, and it recovered it almost perfectly. Okay. So in these examples, it seemed to work pretty good. I redid the first one using distance correlation, and it pretty much recovered the same graph in this case, though presumably, I can't remember now how I simulated it, but I probably used pretty simple distributions. If I used some very, very non-normal distributions, it might be the case that the non-parametric one would pick up the structure much better than the Pearson correlation. But I didn't really test that. All right. Yes?
So in the top right corner of figure 2, is the middle variable just a linear combination of all the others?
No, it's the other way around. I don't remember actually how I generated it, but I'm pretty sure I generated this first. Then I think I took this to be equal to this one plus error, and I took this to be equal to this one plus error.
Wouldn't that make them all correlated then?
They are, and if I had, they are, but they're much more weakly correlated than this is to this. So yes, if I had probably generated more and more and more data, and if I had taken just to be the threshold to be significant or not, eventually these would probably connect up to.
Why is the Markov chain graph is so correlated? It's not like the bottom right.
Well, let's suppose I have a feature here, and I generate a feature given this feature. Then I generate another feature given this feature. These are still correlated.
So how do you get the bottom right?
I don't know why that one came out so good. It just did. Came out much better than I expected. You're right, I expected that one to look like the top left one, but it just had to do with the particular, I made up these examples kind of randomly, so it just happened to be, I guess, the values I chose. Okay. Any other questions then about correlation graphs before we get on to partial correlation graphs? So let's do partial correlations. Partial correlations are much harder to estimate, and they're I sort of think of them as being in between correlation graphs and in conditional independence graphs, although some people treat them as almost the same as conditional independence, but technically it's not quite the same thing, for the same reason that correlation is not the same as independence. So partial correlation, if I have, let's suppose I have feature 1, feature 2, feature 3, I guess I was calling them like this. Now I'm going to make a different graph. For each pair of features, I want to look at the correlation between xj and xk given all the other features, conditional on all the other features. And so for simplicity, let me just write that now as x, y, and z. So think of this as one feature, that's scalar. Think of this as another feature, that's a scalar, and z is everything else. So that's going to be a vector. Of course, we're going to do this for every pair. And why do we want to do this? Well, we want to somehow say, what's the correlation between x and y after adjusting for z, after conditioning for z, conditioning z. Why do we do that? Well, just think about linear regression. If I have a linear regression model with many betas in it, what is the interpretation here of beta 1? Well, it's the relationship between y and x, but conditioning on all the other variables. If I just fit a marginal regression of just y on x1, I wouldn't get beta 1 out, right? It's not the same thing. Beta 1 is the relationship between y and x1, but controlling for all the other variables. It's the same between correlation and partial correlation. Partial correlation is saying after accounting for as much as I can, after accounting for z, how much relationship is left between x and y? Okay, so technically what we do is we take x and we take its projection onto the space, we take its projection onto z, which I'll define for you in a minute. Okay, so I'm taking x and I'm removing as much of z as possible. I'm projecting it out. Did I give that a name? I call this epsilon x. And I do the same for y. I take y and I project it onto z. Okay, what do I mean by this projection? What I mean is the projection of z onto x is beta transpose x, where beta minimizes there's a did I switch something? Okay. Yes. And also I notice in the notes there's another mistake in the notes, which I'll just correct right here. It's beta transpose z. This should be z. Oh boy. Hang on. What am I doing? I wanted to project. This is wrong. I want to project x onto z. This should say z. I'm projecting onto z. I'm taking a linear combination of the z's. And this is x. I'm just asking, if I was trying to predict x from z, what's the best linear predictor, right? What minimizes this? What linear combination of z minimizes the prediction error? That's the projection. And so that's the projection of x onto z. I'm going to remove that from x. Whatever's left over is what's unexplained by z. So there's I guess there's a, oh no, I actually had it right in the notes as usual. Just wrote it on the board wrong. Okay. So if I haven't really explained conditional independence graphs yet, but roughly speaking, it's this. It's like saying we're thinking of x as being generated from z and y is being generated from z, and the correlation that I'm seeing between x and y is due to z. But if I get rid of z, if I take that out, how much correlation is left between x and z? Maybe there's still some correlation between x and z. Does that make some intuitive sense? It's the amount of correlation between x and y after projecting out z. If the only relationship between x and y is due because they're indirectly related to z, then there'll be zero, that partial correlation. And so the partial correlation is defined to be just the ordinary correlation between these projections, between these residuals after projection. Of course, we're really going to do this in the graph for d variables, and we're going to compute the partial correlation for every pair of variables. This is the most common thing after doing correlations, is to do partial correlations. It really is like, think about it like regression. It's like saying, I'm going to regress x onto z and get the residuals, what's left over, regress y and z, get the residuals, and now look at the correlation of the residuals. Is there anything left, any relationship left after we regress on z? That's what's being asked. Now, the question is, how do I write down an explicit expression for this, and how do I estimate it? And that turns out to be surprisingly simple. Writing it down is simple. Estimating it turns out to be hard. So let me explain. So let's define Rjk to be the partial correlation, as I've just defined it, between x of j, x of k, given the other variables, given the rest. So we're trying to, in each pair of nodes in the graph, we want the partial correlation between those two nodes given all the other variables. That's what we want to compute. So this is a matrix now, a D by D matrix. And it turns out that there's a nice simple formula, which is simply this. So despite the kind of long definition we gave there, it can be shown that algebraically there's a simple expression for the partial correlation. What you do is you take the covariance matrix, you invert it, and then the JK partial correlation is nothing other than minus the JK element of the inverse with some normalization. That's the partial correlation. That's the true population quantity you're trying to estimate. But you can already see why it's more difficult than regular correlations, because it involves the inverse of a matrix. Inverse of a matrix, makes us a bit nervous, right? It's from a computational point of view, things are more unstable. From a statistical point of view, inverses are much harder to estimate than the matrix itself. But at least we know what it is we're trying to estimate. And in fact, this suggests, right, how we should estimate this guy. The sample partial correlation is defined in the obvious way. Which is, this will be the sample covariance matrix, the usual sample covariance matrix. And we're now going to take, let me use the same notation, I guess R hat is simply the same thing where omega hat. Now, if the dimension is fixed, what do we know? Actually, we're going to, later, another thing we're probably going to do in the course in the remaining time is we might do a little bit of random matrix theory. We've done random vectors throughout 705 and throughout this course. We haven't said anything really about random matrices. But using random matrix theory, it's possible to show that S hat is a pretty good estimator of sigma. Does that imply S hat inverse is a good estimator of sigma inverse? The answer is not necessarily, because again, taking the inverse is a very delicate operation, especially if the dimension gets big. But let's focus right now on the low dimensional case. We're going to come to the high dimensional case at the end of the class, or I guess maybe on Thursday, depending on how far we get. So for now, let's focus on the low dimensional case. That is, let's keep the dimension fixed, and let's imagine n getting large. Then we can argue by the continuous mapping theorem that this is a consistent estimator. This is a consistent estimator of the partial correlation. We get central limit theorems. We can basically do the same thing we did from the Pearson correlation. What ends up happening, remember how we did the Pearson correlation? The easy way was to do that Fisher transform. Fisher also pointed out you could do this for partial correlations. There's one small change. So if I just do the same transformation on the partial correlations, then this is approximately normal with some mean, which corresponds to the Fisher transformation of the partial correlation. But the variance, remember, I had was 1 over n minus 3. Now it's n minus, it's actually d minus 5. Notice what happens when d is big. When d starts to get close to n, that variance gets big. And that's just telling you what we've been saying intuitively all along, which is that partial correlations are much harder to estimate than correlations. Right? So the variance of the partial correlation, of the estimated partial correlation, is of order 1 over n minus d. That's a sign that when the dimension starts to get large, partial correlations are hard to estimate.
Where do you have G in the notes where G is D minus 2? And you just
Oh,
wrote directly?
yeah, what did I do? You're right. So I was just going by memory here. So maybe I got that wrong. It's n minus d minus 2 minus 3, which is n minus d plus 2 minus 3, which is n minus d minus 1, not 5. Yeah. Okay. Thank you. The key is the d, though, right? The presence of the d. So with this normal approximation, we can do a test, a walled test. We can get a confidence interval and so on. But be forewarned that your confidence intervals are going to be much wider, and your test is going to have much less power. So it is an interesting trade-off, because what you're looking for is something more subtle, more interesting in some sense, but it's harder to estimate. And there can be sometimes a lot of similarities between the partial correlation graph, but they can often be, and the correlation graph and the partial correlation graph, but they can often be quite different. Okay, so the question is, though, what should we do for this partial correlation if d is large? It's clear that when d is bigger than n, this isn't going to work. In fact, you can't even invert the matrix when d is bigger than n. Okay, so I know of only 3 possibilities. Well, actually, maybe 3 or 4 for dealing with the high dimensional case. So these are at the bottom of page 11. So one of them is just do correlation graphs. That's almost dimension independent. And it's not exactly the same graph, but there are certain things that are the same. So for example, under certain conditions, you can show that the connected components of the correlation graph and the partial correlation graph are the same, for example. So there'll be certain features of the graph that will be similar. And again, it's easy to estimate even in high dimensions. There's a whole series of papers, though, about saying, well, why don't we do something like what we did in regression? Remember, we did kind of ridge regression that kind of shrunk the beta hats towards 0. And there's a whole bunch of papers about doing that. Instead of taking omega hat to be S inverse, we first shrink S towards some other matrix. And the typical choices are either the identity matrix, or D here is just the diagonal matrix with the correlations on the diagonal to preserve the information on the diagonal. And I put a little bit of information there about what is often used for the choice of epsilon. And more importantly, I put a couple of the key references there, because there's quite a large literature, mostly in the bioinformatics literature, about using this type of shrinkage to try to get a better estimate of omega inverse and then compute partial correlations from that. Okay. The third choice that we're going to get to in a few minutes is the lasso, which is graphical lasso, right? Where's our old friend? Where's our old friend L1, right? And every time we had high dimensions, why not use some sort of L1 penalty? So how does that work? It's quite simple. Instead of just computing the partial correlations of these things, we're going to use a model. We're going to assume normality. And since we have a normal distribution, in fact, we can estimate mu pretty easily, right? We know that the MLE is going to be x bar. So really, the only unknown thing is sigma. Or if you want to think of it in terms of omega, sigma inverse. So what the lasso does is it says, instead of maximizing the log likelihood, this will be the log likelihood as a function of omega, add an L1 penalty. It's exactly like we did in regression. Instead of minimizing least squares, we just added an L1 penalty. But there we were minimizing. Here we're maximizing because it's likelihood, so we subtract a penalty. That's all the lasso does, the graphical lasso. What you get out of this is an estimate of the inverse covariance matrix, sometimes called the precision matrix, but it's going to be sparse. There's going to be zeros. And that's going to tell you exactly which edges not to connect. So every time there's a 0, you don't connect the edges, and every time there's a non-zero, you connect the edges. Now, there is a catch. Well, there's several catches, actually. But one of them is, I still don't know how to pick lambda in this case. Like a really good method for picking lambda, I think, is sort of missing. What people often do is they'll do tenfold cross-validation, and they'll cross-validate the log likelihood function on the held-out data. I think that's kind of a default. In practice, people say that that tends to give very dense graphs, though. And you're trying to find a sparse graph if you can. And there's some other methods have been proposed. What you might want to do, now for you R users, there's a nice R package called Huge for huge graphs. High dimensional undirected graphical estimation. It's actually written by Han Lu, who is a former student here. And it's very nice because you just give it the data and it does everything for you. You don't have to do any thinking. And what this shows you here is a typical output. Is it'll actually has a default value of lambda. I forget how he's picking it. But it'll allow you to try different values. And so you can see what ends up happening, right, is when lambda is sufficiently big, in this case, the top of page 12 here, you get this nice, this is actually, we know what the truth is because this is a simulated example. And it's a bunch of hubs, actually. So the true graph, based on partial correlations, looks like this, and so on. And it actually gets that pretty accurately. But as soon as you start to relax lambda, you get this complete graph, essentially. So it really, the final output really does depend on the choice of lambda. It's quite sensitive to the choice of lambda. I once asked Daniela Witten, she's a very good biostatistician at the University of Washington, and she does a lot of work on this. And I said, in practice, what do you do? How do you pick lambda? She goes, I just start it at infinity, get an empty graph, and then I start turning up the volume, letting it get more and more until the person she's working with, the biologist she's working with, can't take it anymore. It's like, give them as soon as the graph gets too busy to be useful for them, then I stop. So you can do it kind of subjectively like that as well. Now there's a very interesting alternative, though, to the graphical lasso, which actually predates the lasso. Oh, yeah, question. Yeah. Well, unfortunately, there are lots of papers proving properties of the lasso under very, very, very unrealistic assumptions. They satisfy what are called incoherence assumptions, which are very, very unlikely to hold in practice. And so under reasonable conditions, there's very little, I think, you can say theoretically about what the lasso is doing.
In my experience with lasso, it has a very weird trade-off between type 1 error and type 2 error. It doesn't really control for type 1 error the way you expect it to. Do you have an intuition as to why?
Well, there's nothing in the procedure that would even suggest that it should control type 1 error.
It does control type 2 error, so that's the weird thing.
Yeah, I'm sure one could write down conditions under which you could prove those things, but to say anything about it theoretically in general is very difficult. And there's no shortage of papers about them, but I'll just warn you, look very carefully at the assumptions. There's some pretty strange assumptions in those papers. Now, I don't mean that as a criticism of the people writing the papers, because when you're going to investigate something theoretically, to make any progress at all, especially on something difficult, you're going to have to start by making assumptions. So it's, that's how you make some theoretical inroads into this. But they're not assumptions that are going to hold in practice. So in practice, I don't know that there's much we can say about the lasso. That's why I have to say I have a strong preference for correlation graphs, because I think we do understand them theoretically, and they don't require strong assumptions. Another thing you might do, by the way, is do some sort of dimension reduction first, then do the graph. And that's going to be the next topic, is dimension reduction. That's something that's often overlooked. Is that, one way to deal with a high-dimensional problem is not to just throw our techniques directly at it, but first to do some sort of dimension reduction. All right, let me mention one more thing, though, which is, I think, quite interesting, which is before the Glasso came out, just before it came out, there was a paper by Peter Buhlmann and Nikolai Meinchausen where they did sparse graph estimation in high dimensions using a slightly different technique, and it doesn't quite give the same answers. And let me explain it. I'll just explain what the procedure does. Suppose we're trying to do some sort of sparse partial correlation estimation. Instead of doing the Glasso, here's what you do. That wasn't a very interesting graph, maybe, but let me just actually put the variables like this. Here's what you do. Here's the procedure. And what I like about this procedure is, first of all, it's very easy to program yourself. You don't have to know convex optimization like you do have to know if you want to do the Glasso. So it's very easy to program yourself, but it's also, I think, this has a clear intuitive meaning, which is what I do is I take every possible feature. So I start with this feature, and I say, what would happen if I just regressed it on the rest of these variables? Just do regression. Now, how do we do high-dimensional regression? Remember, there's supposed to be a lot of dots here, okay? You just do the lasso or forward stepwise regression, whatever your favorite sparse regression technique is. So what you do is you do this variable, you regress it on all the other variables, okay? Now, I take this guy, and I do the same thing. I regress this on all the other variables. Then I take this, and I do all the variables. So I do D separate regressions. And now I can ask for any pair of nodes. When I regress this on this, was this a non-zero beta? And when I regress this on this, was this a non-zero beta? And if the answer is yes, then I put a line here. Okay, this is called node-wise regression. For each node, you do a regression. This allows you to take everything you know about regression and transfer it to estimating graphs. And it's actually a way of interpreting graphs. I mean, after all, another way to think about these graphs is the things it's connected to should be good predictors of this. That's another way to think about this. In fact, this package, I think by default, might even use that method because I think it's actually faster than doing the Glasso, which involves, again, a convex optimization. Whereas the lasso, there's much faster methods. So you have in this package, I know, the option, though, I think, to do the Glasso or the node-wise regression. In many cases, they give similar results, but I have to tell you, they don't always give the same results.
So for this one, wouldn't the betas be like symmetric? I mean, at least kind of.
Not quite, because they might be selecting different variables. But even if I regress x on y and y and x, you don't get the same beta. Yeah. All right. So I think of these as all different ways of doing partial correlation graphs. But now let's take the final plunge. Let's go all the way and talk about conditional independence, which is much more interesting, but also even a bit more difficult. Okay, any questions before I go on? All right. So the ultimate graph, in some sense, which really captures information well, is what we should look at, perhaps, is whether xj is independent of xk, conditional on the rest of the variables. Let's just say conditional on the rest of the variables. If they're independent, conditional on the rest of the variables, we don't connect them. And if they're otherwise, we connect them. So the graph might look like this. So this is the graph that says conditional on z, x and y are independent because there's no edge. Okay, and that's in some sense much more informative than just correlations, because after all, correlations, think about generating z and then generating x is equal to z plus error and y is equal to z plus error, then these two are conditionally independent given z. Once I condition on z, they're independent. However, they're going to be correlated. So if I did an independence graph and get the right answer, I'll get this. If I do a correlation graph, I might end up connecting them. But the correlation is due to the path through z.
Can you achieve that by doing partial correlation graph and use a strong correlation method?
Yeah, that's very good thinking. So what's the connection between partial correlation and conditional independence? If I had some notion of strong partial correlation, which checked the partial correlation between these given the others in a non-parametric way, then just like for correlation, that would give me back the conditional independence. So let's work up to that. Let's start by, what we're going to do is talk about, because this is very difficult to find out whether this statement is true or not is extremely difficult. Okay? And so we're going to do it first by making lots of assumptions. We'll assume normality, or we'll deal with discrete variables where it's much easier. Then we'll turn to your question about how do we do it non-parametrically. It's another of many things I've talked about in this course that I still consider to be kind of an open problem, because I don't know really of a good way to do what you've just suggested. At least a successful implementation of it. Yeah. Yeah.
I mean, shouldn't it be impossible to have a general conditional independence test? As a complex property? Completely general, right? No assumptions on the.
Not necessarily. It's a matter of how efficient it would be. Because if I can estimate, if it was only 3 variables, x, y, and z, and I can consistently estimate the joint distribution, once I have the joint distribution, I have everything there is to know about the joint distribution.
The dependence, so if the conditioning variable is sufficiently complex, right, it's always made.
That's why when we get to it, I'm going to say it's really hard to do. That's exactly right. But let's start with some easy cases. Okay, if there are cases where it's doable. Okay. So before we get to non-parametric, let's just stick with parametric. The first one, well, everything works well when what? When the data are normal, right? So if we have that x is normal mu sigma, here's a very simple theorem, but a very useful theorem, which is that just like for normals, correlation and dependence are the same thing. It's the same with partial correlations. So xj is independent of xk given the rest, if and only if the partial correlation is 0. So in the special case of a normal, checking whether a partial correlation is 0 is the same as checking conditional independence. And it's not surprising, right? If there's one time they're going to be the same, it's going to be in the normal distribution. So everything we said about partial correlation graphs, you can think of as a statement about conditional independence under the assumption of normality. And that's the way it's usually cast, in fact. Most people think of doing the glass O as the way they're picturing it is the glass O is telling them which things are conditionally independent of which other things. The zeros in the omega matrix are giving them the conditional independencies. But you have to keep in mind that's only true under the assumption that the data are multivariate normal. In general, it's not true. There is another case, though, where we can do it exactly. I mean, truly get the conditional independence, which are multinomials. And here, I want to talk about a way of dealing with multinomial distributions, which is really, really useful if you're interested in conditional independence. The way we usually think of a multinomial is it's just, what is a multinomial? You know, it's just I have x is x1, x2, up to xk, and there's some probability p1, p2. So it's just a discrete random variable where I've observed it can take k different categories, like k colors, and there's some probability p1 that there'll be color will be red, p2 is the probability that something is green, and so on. And these are just the counts, you know, and the likelihood function is just pj to the xj. That's how we usually think of multinomials. And we know what the MLE is. The MLE of pj hat is just xj over n. Very simple. However, for dealing with conditional independence, the nice thing about multinomials is we can do good inferences for conditional independence, but not if we express it this way. Let me explain what I mean by that. So suppose I have two covariates, x1, which takes values in 0, 1, and x2, let's say that's also binary. Mostly when I talk about these log linear models I'm about to talk about, I'll restrict myself to the binary case for simplicity, but in general these could actually be any discrete variable. So what is this? This means that on each person I'm measuring two things, but it's really a multinomial, because when I measure something on you, it can either be a 0, 0, it could be a 0, 1, a 1, 0, or a 1, 1. So I'm measuring, say, whether you have two different conditions, and you either don't have either condition, you have the second condition, you have the first condition, and you have both diseases. But what is this? This is a multinomial with 4 categories. I could have called this, don't want to overload notation, but let's say category 1, category 2, category 3, category 4, with probability P1, P2, P3, P4. Okay, my point is that when you have several variables measured on each person, but each one is discrete, you can stretch it out and think of it as a multinomial. But just thinking of it as a multinomial is not so helpful in terms of asking questions like, is x1 independent of x2? Or if you had 3 variables, is x1 independent of x2 given x3? How do I express that in multinomial land? It's better to think about it as a table, where x1 can take the value 0, 1, x2 can take the value 0, 1, and I'm going to call the probability series P0, 0, P0, 1, P1, 0, P1, 1. Again, this is just some multinomial, P1, 0. And we want to find, what log linear modeling is all about, is finding a way to re-express the multinomial in a different parameterization so that it becomes trivial to talk about dependence and conditional independence. Let's just think about even this case. Let's just think about these 2 variables. What is this? This is 4 numbers that are positive and sum to 1. So they're on the 3-dimensional simplex, right? Now I can't draw the 3-dimensional simplex, so I'll draw the 2-dimensional simplex. So think of that as the set of all 4 vectors that sum up to 1. What does it mean to say they're independent? Well, independence would be some sort of algebraic restriction, namely that when I sum up the probabilities here and sum up the probabilities here, then if I multiply that by that, I get back that, right? That's what independence is, that the joint distribution is the product of the marginals. In other words, it's kind of a complicated thing, because I'm saying that P0, 0 plus P1, 0, that's this margin, that times this, what's this one? That's P0, 0 plus P0, 1. They're independent means when I multiply those, I get back this, which is some sort of polynomial restriction. The set of vectors on that simplex that satisfies this is some sort of weird polynomial thing. It's something like this. It's called the independent surface. More generally, imagine I had 18 variables, and I want to know, is variable 1 and 2 conditional independent of variable 5 and 7 given variable 18, 13, and 12? If you were to write that out in terms of the multinomial, it's going to be some incredibly complicated set of polynomial restrictions. So how in the world are we going to express that, and how in the world are we going to test it, and so on? Does that make sense? That we want to talk about conditional independence, but just even though they're multinomials, it may be difficult. Well, the genius idea here, which is a simple but very clever idea, is simply to reparameterize the model. And the magic is we're going to start with this giant multinomial. In general, this p could be quite long. We're going to create a new vector called beta. And think of it as just a reparameterization. You give me p and I can construct beta. And conversely, if you give me beta, I can reconstruct p. So I'm not doing anything. I'm just reparameterizing the problem. But the beautiful thing is that the betas will have direct interpretations in terms of independence and conditional independence. And in particular, when I give you the betas, you can read the graph right off the betas. Okay, so this is the nice thing about these conditional independence models, these log linear models. It's called the log linear representation. So we're going to, in fact, I'm going to do it first in just this two-dimensional case. So the way I wrote it here was calling this P of x1, just like over there, right? That's the probability x1 equals some, let's just, let me get lazy and start writing it like this. It's only 4 possible numbers. P0, 0, I'll put them in the table form, P0, 1. All right, now here comes the trick, which is trivial in this case, but starts to get a bit more complicated when we get to more variables. I'm simply going to define the following thing. I'm going to say log of P x1, x2. That's these things. I'm going to define beta 0, beta 1, beta 2, and beta 1, 2. And you can see now why is it called a log linear model, because when you take the log of the probabilities, it's a linear model. It looks just like regression. So I claim by writing this down, I've defined the betas, because when I put in 0, 0 here, that says that log of P0, 0, let's just see, log of P0, 0, well, everything gets wiped out. It's beta 0. So I've just told you what beta 0 is. It's log of P0, 0. And I can keep going, right? I can now put in P0, 1, P1, 0, P1, 1, and you can solve for them. And I've given them for you all on page 14 there. If you just solve these 4 equations, beta 1 is log of P1, 0, P0, 0, and so on. So the point is, if you give me the betas, I can find the p's, right? But now I'm showing you if you give me the p's, I can find the betas. The most important one is this one, though. Look what happens. Just by doing this and solving, look what beta 1, 2 is. It's log of P1, 1, P0, 0, P0, 1, and P1, 0. What is that? If I go back to that table, what this beta 1, 2 is this number times this number divided by this number times this number. And you can check very easily the following thing. x1 is independent of x2 if and only if beta 1, 2 is 0. Just a little algebra to do to check that.
What is this small x1? It's not the same as you write it.
Yes, it is. It's the same, yeah.
It's the feature.
It's the features, 2 features, yeah. Two binary features, yeah.
But you write on the left side, the x here is the count. You count the number.
Oh, sorry about that. You are correct. Forget this one. Now I'm just doing the random variable. You're right, that was a mistake. This is just a single random variable. So I take one of you at random and I measure 2 features. It can only be 0, 0, 0, 1, 1, 0, 1, 1. That's the possible outcomes.
X1 and x2 are binary.
These are both binary, that's right. So x1 can be 0, 1, x2 can be 0, 1. And so there's 4 probabilities that sum up to 1. And I've just re-expressed that log probability as a linear equation in the x's. And again, you give me those betas and I can give you back the p's. You give me the p's, I can get the betas. It doesn't matter. So imagine you were doing maximum likelihood. If you now give me the data, I can compute the likelihood as a function of p or beta because it's 1 to 1. And in particular, since I can get out the p hats, I can get out the beta hats. In fact, there are very efficient algorithms for getting the beta hats. That's much more informative than getting it in terms of multinomials, because look, if I can test whether this is 0 or not, I have a test for whether it's independent or not. And that will tell me whether the graph, in this case, there's only 2 possible graphs. I realize this is a trivial case, but if we understand the log linear model in this case first, it's better to do that than to go on to the general case. I just want to make sure that the simple case is clear. How are we doing on time? Okay. Is everyone, is this, I want to make sure this is clear.
I got confusion. How do you represent the likelihood function
Oh.
for multinomial into that way?
Okay, good. That's a good question. Let's figure out. So let's actually do that. So we have person 1, 2, 3, 4, 5, and so on up to n, right? What's a typical data point? Maybe this person looks like this. This is a 0, 0. Maybe this guy was a 0, 1. Maybe this guy was a 0, 1, da, 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 right? You can think of this now in this table. You can put the counts here. Maybe there was 5 people who were 0, 0s, 7 people were 0, 1s, 8 people were 1, 0s, and 13 were 1, 1s. Okay, I'm just writing down the counts. What would the likelihood function be for p? Remember, p is a vector. I'll write it like this: p0, 0, p0, 1, p1, 0, p1, 1. Well, it's just p0, 0 to the 5, p 0, 1 to the 7, p 1, 0 to the 8, and p 1, 1 to the 13. Right? That's just the usual multinomial likelihood with 4 variables. However, I can think of this as a likelihood function for beta in the following sense. Imagine the computer, for any vector of betas, beta here, remember, is beta 0, beta 1, beta 2, and beta 1, 2. Imagine you were doing, this isn't how it's done, but imagine you were writing a program, you were doing, say, a grid search over beta. For every possible beta, you can compute the corresponding p's. We have the equations. And since you can compute the p's, you can now compute the likelihood. Therefore, you've computed the likelihood for beta. Just compute it, convert b to p, and compute this function. And therefore, you have the likelihood function of beta, and you have the log likelihood function of beta.
So the expression you write here is not a likelihood. It's just a table to map the beta.
That's all it is. You're correct. It's I was just reparameterizing the simplex, which is the p's, and the betas, and I'm just giving you the mapping that goes between the two. And it turns out there's actually, this is not just for interpretability, but there are algorithms that take advantage of this, the beta expression, that make computing the MLE fast. But it's an easy MLE to compute anyway. It turns out it's a concave likelihood, so it's a very easy likelihood to maximize. So now given this data set, I can compute the log likelihood, and I can get out beta hat. It's also very easy, and the software will do this for you, to compute the Fisher information matrix. It's kind of a mess to write down, actually, but it's numerically very easy to compute. So what I get out, if I want to test whether these are independent. Now, of course, for 2 binary random variables, this is overkill, right? The advantage of this is it's going to work in general. But if I just want to test whether these two variables are independent, one way to do it now is to test this, is simply to take beta 1 hat minus 0 over its standard error. This comes out of the Fisher information matrix. And if I want a confidence interval, I just do this. But you can see how much simpler it is to think about, right? This is just thinking about independence is just thinking about whether beta 1, 2 is 0 or not. Whereas if I go back to this multinomial, independence refers to some weird nonlinear surface in the simplex. It's very hard to think about. So there's a huge gain in interpretability by switching to this log linear representation. Okay, and this is another one of these things. I'm sorry I can't tell you how to do it in MATLAB, but it's called, there's a few functions in R that will do it. One of them is called GLM for generalized linear model. The generalized refers to the fact that there are many types of linear models, such as log linear models. So you just give it the right option, and it'll know you're dealing with count data, multinomial data. And I'm sure there's a MATLAB function that fits log linear models. I don't know what it is. So, but now let's talk about the general case. What makes this interesting is it extends immediately. Oh, was there a question? No? Oh, sorry, I thought I heard a question. Immediately we can go to high dimensional, or at least multi-dimensional cases. So now, let's suppose I have a multi-dimensional vector. Okay, and for simplicity, again, I'm going to assume that each feature is binary. It doesn't have to be. It can be just anything discrete, any discrete random variable. But I'm going to take binary. We can do exactly the same thing. The log linear, so we're going to have a probability function. So what is this really saying, right? On each person, I'm measuring d things. So you can think of it as, like my outcome might be 0, 1, 0, 0. Just think of it as a sequence of bits. And how many categories does this multinomial have then? 2 to the d. That's right. So it's a big multinomial. But the log linear expansion is very simple. It's just this. I think you can see what's going to happen here. These are called domain effects. These are called the two-way interactions. This is how pairs of variables affect the probabilities. This is how triples of variables affect the probabilities, and so on. Up to the very last one is going to be, we'll call it beta 1d, x1 times x2 to xd. Once again, this is nothing but a reparameterization of the joint distribution of d discrete random variables. You can think of it as a giant multinomial now with 2 to the d categories and a bunch of p's, or in terms of this log linear model, in terms of a bunch of betas, and you can go back and forth between the two. But it's very fast to do maximum likelihood this way. And the remaining question, which I guess we'll address Thursday, is once I fit this model and get the betas, how do I now interpret conditional independence? How do I get the conditional independence graph from this? And we'll see on Thursday, it's extremely simple, which wouldn't be the case if I had just done it as a multinomial. That's the important point. So what we'll do is, I'm taking longer on graphs than I thought, but I think that's okay because I think graphical models are an important topic. So on Thursday, I want to finish log linear models. Then I want to talk a little bit about non-parametric graphical models. And then I want to talk a little bit more deeply about the notion of conditional independence. Okay? And then we'll do dimension reduction and random projections, and then we'll see what happens after that. Any questions? Okay, see you Thursday.